We're going to look at how to solve an Atwood machine problem. I'm going to do this two different ways. The first way I'm going to do it is with the two method system, or the two system method, and the second way will be the one system method. So we need to set our two systems. This is a modified Atwood machine, so the 4 kilogram block is sitting on the table and there is friction between the table and the block. The 2 kilogram block is hanging freely on the string. We're assuming that the pulley is massless and frictionless, so we need to find the tension in the string and the acceleration of the system. So I'm going to draw my two force diagrams. So my force diagram from my 4 kilogram block, I have a force of gravity acting down. I have the force of normal force acting up. Those are the same size. And then I have a tension force acting to the right. And I have a frictional force acting to the left. And the system is accelerating to the right, so my tension force should be longer than my frictional force. Then my force diagram for the 2 kilogram block, I've got force of gravity acting down and force of tension acting up. And I didn't really draw this completely to scale because my two forces of tension should be equal in size, but that'll be okay. Now I'm going to choose a positive direction for this, and a pulley acts to bend the basically bend the positive direction. It changes the direction of the tension force without changing the magnitude of the tension force. So down is going to be positive for my 2 kilogram block, and to the right is going to be positive for my 4 kilogram block. The next thing I'm going to do is, I'm actually going to call this block A and this block B for our, so we can keep those forces of gravity separate. So now, just like with any force problem, I'm going to I'm going to use my force diagrams to write net force equations. So I'm going to write these without vectors, so we're just going to do the sum of the forces on A is equal to the force of tension, which acts in the positive direction, minus the force of friction. So notice that I'm putting the direction of the force of friction in that negative sign. And then we have the sum of the forces acting on B equal to the force of gravity on B minus the force of tension, because gravity acts in the positive direction for B and tension acts in the negative direction for B. And then I'm going to substitute mass of A times acceleration in for the net force, the sum of the forces on A equals force of tension minus force of friction. My equation for force of friction is mu times the normal force. And then for B, I have mass B times acceleration equals mass B times gravitational field strength minus force of tension. I've got to expand my normal force a little bit more. So if I go back up here, I can see that the net force in the y direction, so the sum of the forces on A in the y direction, is equal to 0. And because that is the case, we know that the magnitude of the force of gravity on A is equal to the normal force. So we can plug in the mass of A times gravitational field strength for normal force. So that'll be mg. And so now I've basically got two equations and two variables. My variables are acceleration and force of tension. So I have a system of equations. And from here, you've basically done the physics, and now you have to do some algebra. Now you can use substitution, but an easy thing that happens when you solve the problem this way is you can add the two equations. And you'll see that you have a negative force of tension over here and a positive force of tension on the other side. And so when you add your two equations, those forces of tension will go away. And that's a nice way to help you isolate one of the variables. So let's add them together. So we get ma times acceleration. We add the left sides, so we add mb times acceleration equals, and then we add the right side. So force of tension minus mu times mass times gravitational field strength. Ooh, this is mass A. We gotta add that in there. And then we add the right side, so mass B times gravitational field strength minus force of tension. So we can cancel out these forces of tension because there's one positive and one negative. And now we need to solve for acceleration. So I'm going to pull my acceleration out. So we get acceleration times mass A plus mass B equals, I'm going to rearrange that so we get, oh, and I'm going to pull out G. So we get mass B minus mu times mass A times G. So I basically just rearranged that right there and factored out our G. And then we divide by mass A plus, mass B. So we're going to divide both sides of the equation. And then we can get it to cancel on the left side. So now we have isolated acceleration. So we get acceleration equals mass B minus mu times mass A times G over mass A plus mass B. So I can plug in numbers now. My mass B was 2 kilograms. My mu was 0.2. Mass A was 4 kilograms. We're going to use 9.8 newtons per kilogram for G, gravitational field strength. Then we divide by 2 kilograms plus 4 kilograms. And when you work that out, you get acceleration is equal to 1.96 meters per second squared. So that's the acceleration of the system. Now, just like with any algebra system of equations, once you solve for one of your variables, you can take that and plug it into one of these two equations up here to find your tension. Oops, sorry, not those two. Those are the same equation. One, either this equation or this equation we can plug it into. I'm going to choose to plug it into this one. So mass A times A equals force of tension minus mu times normal force. All right, so we have mass A times acceleration equals force of tension minus mu ma times g. And I solve for force of tension, so force of tension equals ma times acceleration plus mu times ma times g, because I'm adding this to both sides. And then I just plug in numbers. So mass A is, actually we could simplify this a little bit more. You don't have to do this, you can plug in numbers if you want. But, okay, so then mass A is 4 kilograms, and then we plug in our acceleration we solved for, which is 1.96 meters per second squared, and then we add our coefficient of friction, which is 0.2, times our gravitational field strength, which is 9.8 newtons per kilogram. And then when we solve that out, we should get 15.7 newtons. All right, so those are our answers. Now let's try doing this problem with one system. So this time I'm going to change it up a little bit, and I'm going to say that this whole thing is in my system. I'm going to include the string in my system. I'm still going to choose a positive direction, and that positive direction is going to be bent. But now what I'm going to do is kind of unfold my system. Since the pulley simply changes the direction of the force, then I can redraw it with it unfolded, and now I can draw my forces on this. So here I have force of gravity acting this way, force of gravity on B, and then I have on A, I have force of friction and I have force of gravity, and I have normal force. And those are going to be equal. They are balanced. So I'm going to make this force of gravity on B a little bit longer to show that it's bigger than the frictional force. So now, since I have the string in my system, it's not going to go on my force diagram, the tension force, or in my equation. And the reason for that is that it is an internal force. So remember, only external forces go on our force diagrams. So now when I write my net force equation, I'm going to write this without vectors again. So the sum of the forces on the system equal force of gravity on B minus the force of friction on A. And then I know that the sum of the forces is, according to Newton's second law, is equal to mass times acceleration. But we have both masses in our system. So we take mass A plus mass B, and then we multiply that by the acceleration. And that's equal to the force of gravity on B, which is mass B times gravitational field strength. We don't include the mass A on this part because the force of gravity on A is canceled out by the normal force. So it does not contribute to acceleration. And then we subtract the force of friction on A, which is equal to mu times the normal force on A. And we know from our last set that since the sum of the forces on A in the y direction is equal to 0, the magnitude of the force of gravity on A is equal to the magnitude of the normal force on A. They are in opposite directions, though. So then this is going to be mass of A times gravitational field strength. So we can rewrite that as mass A plus mass B times acceleration equals mass B times gravitational field strength minus mu times mass A times gravitational field strength. And then we've just got to solve for A. So we divide each side by mass A plus mass B, and we get A equals, and then I'm also going to pull out my G up here. So mass B minus mu times mass A divided by mass A plus mass B. And so you'll notice that this is the same equation as the one that we got over here. Right here. And so we got that equation just using one system instead of two. So when we plug in numbers, we're going to get the same exact acceleration. And I'm not going to do that whole part right now, but we should get 1.96 meters per second squared, because you can see that it's the same equation that we got on the other page. Now for this one, we need to solve for a force of tension. And in order to do that, we have to set a different system, because with this first system we've set, the string is in the system, and so it can't be in the net force equation. So just pick one of your masses, it doesn't matter which one, and set a new system. And I'm just going to put an arrow because we're going to solve this down at the bottom of the page here. So on that one, block A, we have force of gravity on A, we have normal force on A, we have the force of tension, and we have the force of friction. So when we write an equation for the sum of the forces on A, we're not going to use vectors, so we get force of tension minus force of friction. And then this becomes mass A times acceleration because of Newton's second law. We have force of tension there. We subtract mu times the normal force. And once again, the sum of the forces in the y direction is 0. So normal force is equal to mg. And we're going to solve for force of tension. So we get force of tension equals, we'll add mu times normal force to both sides. So we get ma times acceleration plus mu times ma times g. And then you just plug in numbers. You'll see that this is the same equation that we had on the previous page when we solved for tension. Right here. That's the same equation. So you're going to get the same value for force of tension, which is 15.7 newtons. So those are two methods for solving the Atwood machine problems. Now, I used a modified Atwood machine, but this is applicable for any Atwood machines. So if you had an Atwood machine that looked like this, where this was block A and this was block B, then you're looking at the force of gravity on A and the force of gravity on B instead of a force of friction and a force of gravity. You could have something where it's on an inclined plane and you have one block hanging off the edge and one block here. And in that situation, you would just have a component of your force of gravity causing the acceleration. So that would be Fgx on A, and then force of gravity on B. So those would be the two forces affecting your acceleration. So it just depends on the situation, but you can apply the same logic for both of them.